Now that we've looked a little bit at Eulerian circuits and Eulerian trails, we're going to try to create an algorithm that constructs an Eulerian circuit in a graph where that is possible. So first we're going to review the theorem that we looked at in class that describes the graphs that have Eulerian circuits and trails. And then we're going to describe an algorithm that completes the proof of the theorem that refers to Eulerian circuits. So let's see if we can remember what the theorem says. Our assumption is that G is a connected graph. Then G has an Eulerian circuit precisely when every vertex of G has even degree, and G has an Eulerian trail that is not a circuit precisely when we have exactly two vertices of odd degree and the other vertices have even degree. So here's the part that we have proved so far. We have proved that if G has an Eulerian circuit, then every vertex has even degree, and we have prove that if G has an Eulerian trail that is not a circuit, there are exactly two vertices that have odd degree. So note that these are both if and only if theorems, so we have another direction that we have to prove. We are going to prove the other direction on part one of that theorem. So in other words, we're going to assume that every vertex of G has even degree, and we're going to prove that G has an Eulerian circuit. And we're going to do that by creating an algorithm that actually constructs that Eulerian circuit and prove that that algorithm always gives us that Eulerian circuit. So here's the strategy that we're going to use with our algorithm. First of all, we don't even know anything about this graph except that every vertex has even degree. So instead of being completely ambitious and trying to find an Eulerian circuit right off the bat, we're just going to find any circuit that we can. So we'll find a circuit, we'll call it C1. Then what we're going to do is we're going to put a pin in that and then come back and try to create another circuit, C2, that just shares one vertex with C1, but no edges. And then what we're going to do is take those two circuits, C1 and C2, and sort of paste them together into one circuit. And here's what that circuit is going to look like, kind of, conceptually at least, not literally. But it's going to look a little bit, I envision it as kind of a figure eight, where V is the part of the figure eight that is right at the intersection of those two circles. So C1 goes around the left-hand side of V, C2 goes around the right-hand side, and we're going to put those together with V is going to be the point where we paste those two together. So if you want to note what that circuit is going to look like, the combined circuit, well, let's suppose that that first circuit, C1, starts at V, then goes to V1 to V2, all the way to some vertex Vn, and then goes back to V. And assume we have another one with C2 that is very similar. Again, it begins and ends at V. So you start at V, you go to some W1, then W2, all the way to Wm, and back to V. And then the question is, well, how are you going to use those two circuits to create a larger circuit? Well, we're going to paste them together using V. So we're going to start with C1, which is V to V1 to V2, all the way to Vn and back to V. Then we're going to go directly from V to the next vertex in C2, which is W1, then to W2, all the way to Wm and back to V. So that it begins and ends at V. All those edges are unique, and so we've taken two smaller circuits, pasted them together into one bigger circuit. All right, so before we actually start describing the algorithm, I want to go through some of the mechanics of what we do when we do a proof by algorithm. So we can't just say this is the algorithm and always works, trust us, right? What we have to do is, well, of course we have to describe each step of the algorithm. We got to describe it precisely, so if someone, say, had to code that algorithm, they'd know how to do it. But then we got to actually say what happens in each step and prove it. We got to prove why each step that we're doing is possible, or maybe even we may have to do both. We have to prove what the result of that step is. So we got to say, we're going to do this next step, here's why we can do it, and here's what happens at the end of that step of the algorithm, and we got to prove everything as we go along. All right, so here's what our Eulerian circuit algorithm is going to look like. So first of all, we're just starting off with a connected graph. All we know about that graph is it's connected and every vertex has even degree. So hard to know where to start on the circuit, isn't it? And every vertex looks just as good as any other. So the first thing is we have to pick some vertex. So I'm just going to pick a vertex V at random. All I know about that vertex is it has even degree. right? Now, one possibility of having even degree is that vertex could have degree 0. And that's a little bit of trouble. That means there's no edges coming out of it. However, actually, it's not as bad as it looks, because if a vertex has degree 0, remember, our graph is connected. So if our vertex doesn't have any edges coming out of it, that means it's not connected to any other vertices. That means if G is connected, V is literally the only vertex in the entire graph. So if I just take the vertex V and just say V, that's an Eulerian circuit. It begins and ends at the same vertex, and it contains every single edge that's possible. There are no edges, so you don't have to have any edges in your Eulerian circuits. So ta-da, there's our Eulerian circuit. So it looked bad when we had a degree 0, but it wasn't as bad as it looked. So if the degree is not 0, that means there is some unused edge that comes out of V. So remember, incident means that edge has V and some other vertex as its unordered pair. All right, so here's what we're going to do. So we know there's an unused edge that comes out of V to something. We'll call it V1. We'll go ahead and travel along that unused edge and then keep track of it, noting that we've already used that edge, because we don't want to use an edge more than once. Remember, we're trying to create a circuit here. And then we're going to keep doing this. Whatever vertex we're at, we're going to keep traveling along an unused edge. I don't care which one, as long as we haven't used it yet. We're going to keep on doing that until we can't do it anymore. In other words, until we get to a vertex where there are maybe some edges coming out of it, but if there are, they're all used up. So there may be unused edges elsewhere in the graph, but at the vertex we are, all the edges have been used. So the question is, where do we end up? And my claim is we ended up exactly where we started at that first vertex V. All right, that's a claim, right? We can't just say, I claim this and trust us. We actually got to prove this. So just for contradiction's sake, pretend that we got trapped at some vertex W with W not equal to V. And remember, we're assuming that W is not equal to V and that there are no edges coming out of W that we haven't traveled through already. Well, let's imagine what's actually happened with W in terms of this circuit that we've been doing. So the first time we get to W is entering through some unused edge. Remember, we started at V, so W is somewhere in the middle of the circuit. So we get to W, and then, but W has even degree. That means whatever happened that first time we got to W, we have to have another edge coming out of it, because otherwise we would have degree 1, which is not even. So that means we can leave through that edge to some other vertex, etc. Now, it's possible that we could come back to W, right? But every time we come back to W through an unused edge, we've traveled to W through an odd number of edges, which means that we have to go out another edge because that the degree of W is even. So every time we come into W, there has to be another unused edge coming out of W, otherwise W would not have even degree. So every time we come into W, we have to be able to leave. That means we can't end the trail at W, because ending the trail at W means we get in there an odd number of times and there's no other edge to come out. But W has even degree, that cannot happen. So if all the vertices that aren't V are impossible to be the end of our Eulerian circuit, the only other possibility is V. That means we end the trail at V. So remember, we don't have the same issues for V as we do for W because we started at V. The first time we leave, that's one edge that we've traveled on. That means we have to come back to V eventually, etc. So every time we go out, we actually have to come back in. So V has kind of the opposite situation as W did. All right? So we've just proved that if we start at V and follow that algorithm, we end up at V at the end. And that means we end our trail on V, which means that we've made a circuit that begins and ends at V. All right, so we travel from V along any other used edge to etc. until we can't travel anymore. And when we've gotten to the end, we end that trail at V. Right? That's the step that we've added there. So now that we've made this circuit that begins at V and ends at V, we ask ourselves, have we used every edge? And of course, there are two answers to that question. One answer could be yes, that would be nice. If we've used every edge, we have a circuit, that's an Eulerian circuit, and we are done. The theorem is proved. But the answer might be no, and that means now we got to figure out how to make that other circuit that we're going to paste together with our first one. So here's what we're going to do. We're going to find a vertex on our circuit that is incident to an edge that we have not used before. Obviously, that edge is not in the circuit that we just made, but we're hoping to find an unused edge that we can start our new circuit from. So, can we do that? Well, we got to prove it. So here's our claim. If we have a circuit C that does not include every edge of the graph G, then one of the vertices on C is incident to an unused edge. So what would it look like if we didn't have, does our picture look like? Well, hopefully our picture looks like what we have over here. I'm going to bring in my pointer here. Over here at W, where W connects to some Z, where this is a new edge, right? That's what we're looking at. But, of course, Peeves says, well, what if all your unused edges are way out here that are not connected to the circuit at all? Well, we've got to consider that possibility and show that we can somehow find the Z that is outside the circuit that connects to W that is inside the circuit. All right, so for contradiction, we have to assume that every unused edge in our graph is not incident to any vertex on that circuit C. And let xy be such an edge. Well, let's see. If that is the case, then certainly x cannot be part of C. If it is, then we have an edge that is incident to a vertex on the circuit C that is to a vertex that is not, right? So x can't be on C. But remember, we know that G is connected, which means that we can make a path between any two vertices in the graph. And I'm going to apply that from x to V. I know there's some walk, some path, where we can start at x and end at V. Now, note that V is a part of our circuit. So that means there is at some point where along that path we're going to enter the circuit, and we're going to let W be the first vertex on the path from x to V, such that W is on the circuit C. Now, that vertex W might be V itself, but it might not. It might be that we enter the circuit along one vertex, travel along the circuit to get along to V, and that's our path from x to V. But whatever it is, W is the first one that we get on. And note that the edge that gets to W, the first edge that takes us to W, that is going to be an unused edge on the circuit, and that proves our claim. That there is an edge coming out of W that we have not used yet on the circuit, that and W is part of the circuit. All right, so we're going to find a vertex W on the circuit that is incident to an unused edge. We've just proved that that is possible. That not is possible, but that has to happen. Right? So here's what our circuit looks like when we start at W. Remember, we have a circuit, so we can start wherever we want. I want to start at W. So it's going to be W. That's going to connect to some other V1, not the same one as we used before, then to some other V2, then all the way to Vn, back to W. Right? That's our circuit C. Now what we're going to do is we're going to repeat step 2, and get a new circuit. So what did we do in step 2? Well, what we did was we traveled from our vertex, in this case it's W, along an unused unused edge, and keep traveling along unused edges until we run out of unused edges to travel along. So when we do that, we're going to get back to W, and what that's going to enable us to do is create a new circuit, W to W1 to W2, all the way to some Wm and back to W. So we're going to do exactly what we did in step 2, except instead of doing it with V, we're going to do it with W. And then we're going to combine the two circuits, as I noted before. We're going to start at W, go through the circuit 1, V1, V2, all the way through Vn and back to W. Then go through circuit 2, W to W1 to W2, all the way to Wm and back to W. And that creates a larger circuit. And then we're going to keep on doing this over and over and over again. Each time we're going to go back to step 3, ask, have we used every edge? If yes, then we're done. If not, then we're going to create another circuit and add more edges to our circuit. And we're going to keep on doing this forever and ever, or until we're able to stop. Question, of course, is, will we ever stop? Or will we get stuck in an infinite loop? Well, remember, each of those steps where we make a new circuit, we add new edges to our circuit. But our graph has finitely many edges, so eventually we're going to run out of edges. That means the algorithm must eventually stop. And now we got to go back to the steps of the algorithm and ask, where does the algorithm stop at all? And there is only exactly one place where the algorithm stops. I'm calling it step 3a, and if you don't remember what that is where we asked, have we covered every edge on the graph? And if the answer is no, we go back through the loop. But if the answer is yes, then we stop. So what that means is if we stop, which we must since we only have finitely many edges, the only place that we could stop is when we have an Eulerian circuit, when we have a circuit that contains all the edges, which proves our theorem. All right, so what you're going to do is you're going to prove the other direction for the Eulerian trail theorem, the one that says if you have an Eulerian trail that is not a circuit, then precisely two vertices have an odd degree. You're going to prove that on your homework using the same principles.